All right, here we are back talking about fluids again. We were just talking about how liquid pressure, if you're in a liquid, is based on the weight density of the liquid and the depth that you're at. And so really it comes down to, most of the time if we're talking about water, since it's usually the liquid we're talking about, it's all about depth. For example, if I wanted to check scuba diving equipment, all right, um, it's how deep below I am below the surface. I could go out in a lake and test it as long as I'm the same depth that I would be in the ocean, and it would still have the same pressure. In fact, they can actually, a lot of testing is done in a tall vertical container that may be in a factory somewhere, but as long as it is full of water, it would have the same pressure that the equal depth would have if you were out in the ocean. Okay, here's the ocean floor down here. Okay, and you would have the same depth. Having more volume of the rest of the ocean around you does not affect it. It's all the pressure of the fluid above you. And so a person testing it down here at the bottom would feel equal pressures either here or out in the ocean. If the depth of water above them is the same, then they would have the same amount of pressure. All right. Uh, Thinking about this, one of the reasons we have water towers then is in order to get the water in the water tower, we have to pump it up. Why would we want to go pump the water all the way up to the top of the water tower? Well, once it's up here, now this water, which runs out to the pipes to our homes, has a height, or depth, if you will, of this much. And so therefore, there's going to be a lot more pressure on it, and therefore it will flow better into your home. The higher the water tower, the more pressure it will have. Then how big the water tower at the top is not really the issue as much as the height that you get it to. You need to get it to this height so that you can have the water pressure that you want for you to get to your home. Now, if water is in a container, and if it's at the same depth in that throughout that container, then we know that it will have the same pressure. And so basically, when you put water in a container, you can see these little, these are connected across the bottom. These are all connected. There's a straight line coming off here off to the side. This one has a little bulb in it. This one has a little curlicue, and this one's just a tube coming up. But you'll notice that the water is at the same level all the way across. Why? Because equal pressure. If this one were taller over here, say the water were up to, say, here, then this would have more pressure. And since it has more pressure, it would push down and push the others up to where they would all be a little bit higher. So if I were to pour a little more water here, it would raise it up to here temporarily, but then the pressure would flow into these other, higher pressure would flow into these other ones until the pressure is the same, and therefore the depth is the same. Notice the shape, or how thick, how far across it is, the volume basically. Here you have a skinny tube, here you have a fat tube. None of that affects it. It's all about pressure. And since pressure depends on depth, the depth or height, depending how you want to look at it, is going to be equal in each of these so that they all have equal pressure. All right. Now, when something is put in water, pressure is exerted in all directions. Okay, for example, here's just a little thing here. And the pressure is always perpendicular to the surface of the object. So here you have a triangle shape, so you're going to have a perpendicular force to this surface pushing in here, perpendicular to this force pushing here, perpendicular here. Technically at the points here you would have a perpendicular force pushing in. And so water is always going to be at a perpendicular to the surface. All right, which means if we take a glass of water and we poke holes in it, where's the liquid going to flow? Well, it's going to flow sideways or horizontal. Now, but if we do that, notice that it starts going down and curving. Why? Because what other forces acting on it besides the pressure of the water? Once it gets out of the container, you have gravity pushing on it, and so that pushes it down. Notice though, which water goes the farthest out or has the most pressure on it? The bottom one, because it's at a lower depth. As you come up here, there's less water pressure on it, and as you get up here toward the top, there's even less water pressure, so it doesn't squirt out very far horizontally before gravity starts pulling it down. And so once again, that's just showing that as you have more depth, you have more pressure. and that the force is pushing perpendicular, so it's going to push it straight out the side, and then gravity will kick in and start pulling it down. All right. Now notice that there is pressure pushing up, there's pressure pushing down on the object, and it goes in all directions. If you tried to push a beach ball, for example, or something below the surface of the water, or maybe your brother or sister's head, or whatever, anyhow, when you're a kid, you will feel there's a water pressure or force pushing up against it, and that's why it's so hard to push it down. So water exerts, or fluid exerts, its pressure in all directions, up, down, and so forth. Okay, and basically the deeper you go, the more pressure there is, therefore the more force, and this water would go out farther, but it also go out faster and squirt out farther before gravity pulls it down. The higher it is from top, less pressure, slower, and gravity pulls it down quicker. Now, this pressure of water putting on objects leads to a thing called buoyancy. Buoyancy, besides just being kind of sometimes something we really kind of misunderstand in some ways. First of all, it's spelled B-U-O-Y, which doesn't look right, buoyancy. But buoyancy has to do with this pressure of water. Now, if you have an object in water, we said that it will have pressure pushing at it on all sides. But the thing is, if it is on the object, the more, especially this is more true, the bigger the object is, the top part of the object is not very deep, so it has a fairly low pressure. Now we kind of exaggerated it for this potato here, or rock, but basically it's not very far below the surface, so it has pressure. But as you go around it and you're getting deeper in the water, there's more pressure till finally on the bottom, because it's deeper, that much more deeper, it's going to have the most pressure on it from the bottom side. And then once again, as you come up this side, you're getting shallower in the water, so it gets less and less pressure. And so there is always going to be more pressure on the bottom of an object than on the top of an object. Okay, and so the net force, if you take the force pushing down on it from water pressure and the force pushing up, the difference between those, the net force, is going to be an upward force. There's always going to be an upward force because there's always more force pushing at it from the bottom, and the bigger the difference between these, the greater the buoyant force is. Okay, and so no matter what you do, the object on the bottom of the object is always going to have, it's deeper in the water, so it has more pressure pushing up against it, and so you will always have a buoyant force pushing up on. So there's always a net force pushing up. Now the question is, how does that affect the object? Will it float or will it sink? And basically it depends on the weight of the object. Okay, because we have the net force between the buoyant force, which is always going to result in upward force. But there's also the downward force of the weight of the object, or gravity. If this is, for example, with this rock, it's a very large object, then the force of gravity is going to be greater. Okay, and therefore the total net force on this object will be to go down. Now, it will not sink as fast as if there were the buoyant force pushing up on it, but it's still going to sink. Okay, it's going to fall slowly, but it's going to fall, or slower, but it's going to still sink. All right. On the other hand, if this was something very light, like a beach ball or something, then its weight would be very small, and therefore the force pushing down would be very small, and the net force would result in it being pushed up to the surface. So if the weight is less than the buoyant force, then it will float. All right. Now, if it were exactly the same, let's just add a little more force here. If its weight were just a little more, these are what we would call kind of buoyant neutral, or they're just going to kind of float. If you were to set it in the middle of the water, it should just sit there. If you were to scoot it down a little farther, then it would just sit there once you let go of it, because the buoyant force is exactly equal to the weight. Now, it's very difficult. If we try to do that, we'll try to do that maybe in lab, but it's very difficult to get it 100% buoyant neutral there, where the forces cancel out. But theoretically, that's what it would do. So basically, that's what the buoyant force equals to. Now, Now, related to this also has to do with something you've probably done in labs before in high school and stuff, and that is displacement. If I put an object in the water, okay, and if I have this completely full and then I put a rock in it, what's going to happen to the water that was there? Well, it's going to push some of the water out over here. All right, and as it turns out, that we're going to find that the amount of liquid that comes out, that gets displaced or pushed out, is going to be exactly equal to the volume of the rock. Okay, and so for some things, we can't do length times width times height to find the volume. So one of the ways we do it is by water displacement. We fill this up full with water, we put an object in it, it pushes water out. If we measure how much water came out, then we know what the volume. We pour this into a graduated cylinder and find its volume. That will be exactly equal to the volume of the rock. And so this is a way to find the volume of what we call irregular objects. First people to realize this part, that if you put an object in here it would displace an equal volume of water, was a Greek scientist, Archimedes, or at least he was I don't know if he'd call himself a scientist at the time, but he was investigating things, and he had been tasked by the king to find out if the crown that the king had just had made, he had a new crown made, and he suspected that perhaps some of the metal in the crown was not gold as it was supposed to be. Perhaps inside the crown were other metals, and then it was just coated with gold to skimp on it and save money. And so he suspected this was true, and he said, gave it to Archimedes and said, "You need to find out how to do this." Well, obviously, cutting into the crown was not an option, because then, yes, you may find out if it was pure gold or not, but you kind of ruined the crown. So somehow Archimedes needed to find out how he could do this. And according to legend, he was sitting down in a bathtub, and as he did, he watched the water come up, and he'd get out, get in, and realize that as his body went in, it displaced a certain volume of water, and it occurred to him that he could use that to find the volume of the crown, and then he could calculate its density, and then based on its density, he could decide if it's really gold or if it's not. Now, also according to legend, he yelled, "Eureka, I've got it," and ran down the street naked because he was so excited. That may or may not be 100% true, but at any rate, it was an important discovery. All right? And basically, he said that when you put an object in water, it's buoyed up by a force equal to the weight of the fluid. So for example, if I put this rock in the water, and let's just say that it displaces 20 milliliters of water, okay, that tells me that the rock has a volume of 20 milliliters or 20 cubic centimeters. Okay, we talked about that earlier. Okay, and the force pushing up on it would be equal to the weight of this water. Okay, and we know that 20 milliliters is the same as 20 grams of water, and to make a force, we multiply that by 10, which is the acceleration of gravity, remember, mass times the force of gravity, or acceleration due to gravity will give you that. So there would be a force of 200 newtons pushing up on this rock. Okay, so the force pushing on the rock is equal to the weight of the volume of water that it displaced. All right, now if the weight of the rock is more than 200 newtons, then it will sink. If it's less than 200 newtons, then it will float, and if it were exactly 200 newtons, then you'd be able to move it around the water and let it go, and it would just stay in that one place. And also, Archimedes found that it didn't matter if you completely immersed it like this, or if you only put part of it. If you only put half the rock in the water, and it only displaced 10 milliliters, then there would be 100 Newton force pushing on it. Then as you drop the lower, as more of the rock goes in the water, more of the water is displaced, therefore the buoyant force would increase until it gets to the full buoyant force of the complete rock, displacing 20 milliliters of water. All right, we will start right there on our next lecture.